It is very difficult. Then how will you find or how will you identify? Today we will discuss conformation of cyclic compound, especially cycloalkanes. In the case of cycloalkanes, very common cycloalkane which is present in natural product is cyclohexane molecule. A cyclohexane will be having a molecular formula C6H12. And a simple structure which can be represented for a cyclohexane is a hexagon structure. When we come to this hexagon structure, we can see that the carbon-carbon bond angle will be 120 degree. But we all know that in the cyclohexane molecule, these carbon atoms are sp3 hybridized. And as it is an sp3 hybridized carbon, they will be showing a bond angle of 109 degree 28 minutes. So what about this molecule? It is possessing a bond angle 120 degree. We should have the desired bond angle should be 109 degree 28 minutes. So this planar structure of cyclohexane will be experiencing or a strain is induced in this ring. In this cyclic ring, a strain is induced due to deviation from the desired bond angle 109 degree 28 minutes to 120 degree. And this type of strains we call angle strain. So due to this angle strain, planar structure of cyclohexane molecule seems to be stable because it will be having maximum energy due to the strain. But we know that cyclohexane molecule are most common in nature. That means it is stable molecule. So how will you explain the stability of a cyclohexane molecule? Sash put forward or introduced the non-planar structure of cyclohexane which overcome this angle strain. And later the theory of strainless ring is put forward by Sash theory, that is Sash and Moore put forward this strainless ring theory. According to that, the cycloalkane molecules will be possessing a non-planar structure. In this case of conformation of cyclohexane molecule, there are several structures possible in this case. So these are some of the conformations of cyclohexane molecule which are having non-planar structure. How they got this much conformation? Because twisting and bending of bond is possible. Twisting and bending of the bond is possible. What is that? It is conformation. So chair, boat, half chair, twisted boat, all are some of the conformations of the cyclohexane molecule. Okay, so what is the difference here? We can see that in the chair conformation, the 4 carbon are in same plane. 1 carbon below the plane and 1 is above the plane. When we come to boat, the 4 carbons are one plane, then the 2 other carbons are above the plane. And in the case of half chair, we can represent half chair in this mode. This is a half chair form. So here all the carbons except one atom is above the plane. And this is a twisted boat form. In this case, the 4 carbon atoms, when we take the 4 carbon atoms, some bonds are out of plane. Okay, so we can analyze which is more stable, which is least stable by using the potential energy diagram of different conformation of cyclohexane molecule. In this, we can see that the chair conformation is having the least energy. Okay, So it is a least energy conformation. When we come to chair, then on twisting, we will be getting a half chair. And this half chair is having a maximum energy. So this will be a minimum stable conformation. And next, on twisting or bending, we will be getting a twisted boat. A twisted boat conformation which can be represented like this. That means the carbon-carbon bonds are crossing to each other. And this twisted boat conformation is having lesser energy than half chair. And next, we will be getting a boat conformation which is having higher energy than twisted boat. And again, we will be getting twisted boat, then to half chair, and then to a chair conformation. So, normally, when we take conformations of cyclohexane molecule, we will be discussing two types of conformations mainly. One is chair conformation and boat conformation. We know that this half chair is having high energy. That means it will be having least stability. Why it is having least stability? Because when we come across other conformations possible, this half chair will be having angle strain. This half chair will be having angle strain as it is possessing a structure just like this. This structure. Or we can represent it as this. Okay. So in these conformations, while we are discussing the energies, we should consider all the strains induced in the ring or destabilizing strains. Which are the main destabilizing strain? One is, of course, angle strain. The others are torsional strain. What is torsional strain? It is the repulsive interaction between bonded electron pairs of adjacent atoms. And here we can see that in this half chair form, the torsional strain is maximum because all these are eclipsed in nature. And apart that torsional strain, we will also discuss about steric strain. Steric strain. So, as it is substituted, it will be showing a nature of a normal butane molecule. So, as there is repulsion due to steric entrance of this methyl group in butane, here also steric strain is possible. So, when we take a half chair conformation, angle strain is there, torsional strain is maximum, and steric strain is maximum. So that's why it is having, the half chair is having maximum energy and minimum stability. And when we come to twisted boat and boat, twisted boat is more stable than boat conformation. Why? Because in this boat conformation, we can see that there is an interaction between these hydrogen. This hydrogen is known as flagpole hydrogen. And the distance between these two hydrogens are smaller than that of van der Waals radii. It is approximately 1.83 angstrom. So they will be experiencing a repulsive interaction, that is van der Waals repulsion. And this repulsion destabilizes the boat form when we compare to that of twisted boat. In the case of twisted boat, we can see that the flagpole hydrogens are far apart. And that's why boat is having more energy than twisted boat. And the least energy is for chair conformation. And normally we used to discuss about two conformations, that are chair conformation and boat conformation of a cyclohexane molecule. Let us go to these two conformation in detail. So this is the chair conformation and this is the boat conformation. See, let us take this model of chair and boat. We know that they are interconvertible. As they are conformational isomers, no need of bond breaking and making. So let us take a chair conformation. That is, 4 carbon atoms are in one plane and 2 above the plane and 1 below the plane. So when we take this, we can see that in this conformation, the 6 carbon hydrogen bonds are parallel to axis of symmetry. So when this is an axis of symmetry, we can see those 3 hydrogen on the facing towards upward or parallel to axis of symmetry, and these 3 towards downwards are parallel to axis of symmetry. Okay, and when we take the other 6 hydrogen, they are on the periphery of the ring. Okay, so when we take 2 adjacent carbon atoms in a chair conformation, we can see that these 2, when we take these 2, we can see that these 2 are in a staggered conform. And when we take these 2 are also in the staggered conformation. And so in this chair conformation, all the adjacent carbon atoms or all the adjacent atoms are substituted and arranged in a staggered form. The torsional strain is minimum. The torsional strain is minimum in the case of chair conformation. And both in boat conformation and chair conformation, there is least angle strain. The tetrahedral, that is 109 degree, 28 minutes, is almost maintained in both forms. So the substituents in the adjacent carbon atoms are as far as possible in the case of chair conformation. Let us take the boat conformation. See, this is the boat conformation. The 4 carbons are in one plane and the 2 carbon are in the upper plane. Here, this is known as, these 2 hydrogens are known as flat pole hydrogen. That I mentioned earlier, the distance between these 2 flat pole hydrogens are 1.83 Armstrong unit. That is less than van der Waals radii. So there will be van der Waals repulsion, or there will be steric strain due to the close spacing of this flat pole carbon. And apart from that, when we take these 2 carbons, that is 5 and 6. What is the peculiarity of 5 and 6? Look, this 5 and 6 is eclipsed. And what about 2 and 3? 2 and 3 is also eclipsed. So when we take 1 and 4, these 2 are 1 and 4. In this case, 1 and 4 hydrogens are flat pole hydrogen, and they will be experiencing a repulsive interaction between the flat pole hydrogen. That means the steric strain is there. Apart from that, this 2 and 3 are eclipsed, then 5 and 6 are also eclipsed. So there will be maximum torsional strain also. So this boat form is less stable than chair form. Why? In chair form, torsional strain is minimum, steric strain is minimum because it is in a gauche normal butane form. In this case, we can say it is in a gauche normal butane form. Okay, whereas here it is an eclipse conformation. They are arranged in an eclipse conformation. Apart from that, the flat pole hydrogen will be having interaction. That's why both form will be having more energy than the chair form as well as twisted boat form. Okay, so these are the main conformations of cyclohexane, chair and boat. And when we compare the stability and the occurrence of different conformation at normal condition, almost 99% chair conformation exists at an equilibrium. So, chair conformation is a dominant conformation of a cyclohexane ring. So, what is it? Cyclohexane possessing a non-planar structure, a puckered ring structure, where twisting and bending of bond is possible. So, different conformations are possible. Among these conformations, most stable conformation is chair conformation. It is having least energy because it is having least angle strain, least torsional strain and least steric strain. And the energy difference between the least energy or most stable chair conformation and the least stable half chair conformation is nearly 43 kilojoules per mole. When we take the energy diagram, we can see that the least stable form is 43 kilojoules per mole energy difference. We can arrange different conformation according to the potential energy diagram. What is the order of stability? Which is more stable? The order of stability is chair conformation is more stable than twisted boat conformation. Twisted boat conformation, which is more stable than boat conformation, and boat is more stable than half chair. Half chair conformation. The energy difference, we know that the least the least energy chair conformation and half chair, the energy stabilization is 42 kilojoules. Whereas when we take chair and boat form, it is 29 kilojoules. When we take the chair and the twisted boat form, it is 23 kilojoules. Okay, so what happens while twisting and bending of bond? What happens? Look here. What's the difference? We can see that this is the chair conformation. This chair conformation will be having two types of hydrogen. Those hydrogen which are parallel to the axis of symmetry is known as axial bond. These all are axial bond. Those hydrogen which are towards the periphery of the ring, or we can see that which are perpendicular to the axis of symmetry, these is away from the ring. This is away from the periphery of the ring, or it is perpendicular to the axis of symmetry, and such bones are known as equatorial bones. So two types of bones are present in a cyclohexane molecule: 6 axial hydrogen and 6 equatorial hydrogen. 6 axial hydrogen and 6 equatorial hydrogen, among which the 3 axial hydrogens are above and 3 are below, pointing downwards and pointing upwards. And similarly, equatorial away from the ring, periphery of the ring. Here, when a cyclohexane molecule undergoing a flipping and twisting, what happens? We can see that the first carbon is here, and when we undergo bending and twisting, the first carbon will be placed in the upper position. That means this axial will be converted to equatorial. This axial will be converted to equatorial and equatorial to axial. This process, that is the conversion of an axial into equatorial, let it be the first carbon. The first carbon will be coming downwards. So this axial will be converted to equatorial and this equatorial to axial. This process is known as flipping. When we take a cyclohexane, chair conformation is the most stable. Almost 99% of chair conformation is there at equilibrium. Normally, it is the predominating conformation of cyclohexane. And in the chair itself, the conformations can be interconvertible, where the axial and equatorial can be changed. The exchange of axial into equatorial is in the rate of 2 into 10 raised to 5 second inverse at 25 degrees, so that it can't be distinguished. We can't distinguish which is axial hydrogen and which is equatorial hydrogen. It is very difficult. Then how will you find or how will you identify there is such axial and equatorial hydrogen? When we take the NMR spectrum at low temperature, around -100 degrees, we will be getting two different peaks. Two different peaks, which shows there is two types of hydrogen in a cyclohexane molecule. Okay, so axial is converted to equatorial and equatorial is converted to axial during flipping, and it takes place in this rate at normal temperature. Here it's the flipping process. During flipping, the chair conformation first converts to half, then to twisted boat, then to boat, then again to twisted boat, then half chair, then it will be coming to a twist, means a flipped form. So this is about the conformation of a cyclohexane molecule. At equilibrium, 99% of chair conformation is there in a cyclohexane molecule. And in chair conformation, there is two types of hydrogen. 6 hydrogens are axial and 6 hydrogens are equatorial. Under normal condition, we can't distinguish these two hydrogen. They are easily interconvertible. That means they are undergoing flipping. And the exchange of axial to equatorial is 2 into 10 raised to 5 second inverse. Okay, so that about conformation of cyclohexane molecule.